All right, so the plan today is just to continue on with differential equations. Um, I'm going to post the supplement in the next day or so. I ran into a couple of things last week that I had to take care of. Um, so in the next, either today or tomorrow, I'll have the supplements on surface area and probability posted, and then supplements on differential equations later this week. So that'll probably be whatever on separable equations we don't get through today, if there's anything we don't get through, the first order linear type of equations, and possibly starting second order. So that'll be the next supplement coming out later this week. And then we should, for the most part, I think, wrap up differential equations between today, Wednesday, and the supplement. The quote of the day is from Dave Ramsey, kind of financial guru guy. Very dogmatic. Some people don't like him because he's really sticks to his guns on certain things. And certainly not great financial advice for everybody, but for the people he's kind of speaking to, I think his advice is pretty good. And one of his quotes that I like is "Desperation precedes stupidity." So in other words, we tend to make decisions at a less high level than we otherwise would when we put ourselves or allow ourselves to get into desperate places. So if you can avoid that, particularly these days with things like Chat GPT and so on, you can imagine that waiting until right before, say, a term paper is due to start writing it, makes it that additional stress and so on, makes it maybe a little more likely to be tempted to do something that you ought not do. So I think that is definitely something that that applies to broadly to human nature, but also to academics. So jumping right into it, last time we discussed quite a bit about direction fields or slope fields, and we're going to work through two more direction fields today by hand, and then we're also going to look at some technology that we can use to draw these to make them a little more efficient, particularly for ones that aren't easy to draw by hand. So these two that I'm going to do by hand, I'm going to go somewhat quickly through because we talked really extensively and thoroughly about making these by hand last time. So the first thing that I note is my differential equation P prime equals Kp minus R. And here P is P of T. So K and R are parameters. And this is an example of a model for population growth with harvesting. So you can think of something like maybe a salmon fishery or something that has kind of a natural population growth like P prime equals Kp, just a Malthusian model where it would grow exponentially, but we have a harvesting term per unit time. We're harvesting a certain number of salmon to, taking them out of the population to turn into food, and the remainder of the population kind of proceeds normally. So we note that this is an autonomous equation. This makes drawing the direction field, the slope field, a little easier. It's autonomous. When we say that, we mean that there's no explicit dependence on the independent variable. So it's not like P prime equals Kp minus R times T or something, where we would say, as we change P and T, the direction or the slope of the tangent lines is going to change. There's no explicit dependence on T. And we saw something we can do to kind of help us a little bit when modeling this is we can look at a picture of P prime versus P. Here we're thinking of K and R as positive numbers. So if I have P prime equals Kp minus R, when P is 0, P prime is negative R. And as I go to the right, as P increases, it has a positive coefficient. So for instance, P prime is 0 whenever P is R over K. And I see that the relationship of P prime with P can be modeled by this line. Furthermore, I see that when P is less than R over K, then P prime is negative, as we can see from the picture, which means that P will tend to go further in the direction to the left of R over K, making P prime more negative, making P go even further to the left, and vice versa. When P is bigger than R over K, P prime is positive. So it seems like P equals R over K is an equilibrium, but it seems like it's an unstable equilibrium. When P equals R over K, P prime equals 0, so then P just stays at R over K forever. But if P deviates from R over K, if our population goes a little below R over K for a specific R and K, then we get a population decline to 0. And if P is bigger than R over K, if we start a little above R over K for whatever those two constants are, then our population just keeps growing. In other words, another way to think of this is if our harvesting rate is too high relative to our natural population growth rate, so that our population at a certain point can't support the high amount of harvesting given its growth rate. Essentially, if we're harvesting more, say, salmon than are born each time period, then over time the population goes to 0. On the other hand, if the population is large enough that the birth rate is large enough that it's above the amount we're harvesting per unit time, if we get more births than removals from harvesting, then the population just keeps climbing, in theory, until it's infinitely large. So that's what we expect to see from this model. So let's actually draw our direction field now. So now I want to draw a graphical representation of P of T, that is the instantaneous rates of change, the little segments of tangent lines to P of T. So here I have, maybe T equals 0, 1, 2, 3. But remember, this is an autonomous equation, so there's no explicit dependence on T. In other words, once I get my slopes drawn for some different values of P, then I can just copy that vertical column of slopes over to the right for each successive time period. I know that P equals R over K is going to be very important. That's where I have a horizontal tangent. That's where P prime is 0. I'll have that same horizontal tangent at these other T values as well. And this is an example where having technology isn't super helpful because I have R and K. My calculator or my website isn't going to be able to really give me a lot of information here because R and K aren't actual numbers. But I do realize that if P is less than R over K, P prime is negative. If P is a little less than R over K, P prime is a little negative. If P is a lot less than R over K, P prime is a lot negative. So if P is a little less than R over K, we'll make it a little negative, a bit of a negative slope. If P is a little more below R over K, we'll have a bit steeper of a negative slope. And similarly, if P is above R over K, if it's a little above, we have a little positive slope. If it's a little more above, we have a little steeper of a positive slope. And if it's even more above, we have an even steeper still positive slope. And then I might draw some sample solution curves. So one solution curve that's important to include would be, of course, the equilibrium solution. P equals R over K, where we're harvesting right at the growth rate. The population just stays constant. Population starting off too low to support our harvesting, or a little lower, or a little lower, or population starting off above what we're harvesting. Something like that. And of course, I mean, my artistic abilities aren't aren't the best, so but I think this gives us a pretty good idea of what these solution curves can look like. We have kind of three regimes. We have an equilibrium, we have the upper regime where the population grows, and the lower regime where the population declines to zero. It actually declines pretty quickly to zero. So it's not like a nice exponential decay to zero or something. It's like a kind of a nosedive to zero. Okay, any questions on that one? So that's a fairly similar one to the one we did last time. Let's look at this one that has a little bit of a monkey wrench thrown into it. So here we have y equals y of x. And my equation is y prime equals x squared plus y squared minus 1. This is not autonomous. In other words, my slopes are going to depend on both the x and the y location, both the horizontal and vertical location of the point where I'm evaluating that slope. So this makes things a little bit more complicated. I suppose I could just go ahead and just try a whole bunch of different x's and y's, just make a bunch of grid points, plug in each x and y, and then evaluate y prime at each of those and try to make a picture that way. That there's, in theory, nothing wrong with that. That's how the computer is going to do it when we look at some of the technology. But it's kind of tedious. It's kind of laborious. Can we come up with a better way of going about this? Well, we want to look for something a little bit like equilibrium solutions. And we call these isoclines. So we use the isocline method to help us draw this, this direction field. Again, not strictly necessary. We could, in theory, just set out a bunch of grid points and evaluate them all. But to be a little slicker, we're going to look for curves along which y prime equals some fixed constant. In other words, if I say, where is y prime equal to 1 or 0 or whatever, that's asking the question, where is x squared plus y squared minus 1 equal that constant? Or in other words, where is x squared plus y squared equal 1 plus c? This is a circle with radius of root 1 plus c. So let me just pick a couple of different values for c. Remember, c is what y prime is. This is the slope. And then I'll figure out the radius. Root 1 plus c. This is the radius of the circle along which the function will have that slope. The solution curve will have that slope. So if I pick c equals, let's say 0, this would be 0 slope, horizontal tangents. That's a circle with radius 1. A slope of, let's say, -1, where the tangent line to any solution curve passing through there would be -1, would have slope -1. that's a radius of 0. That's going to be just the point at the origin. Maybe something like -1/2. Well, 1 minus a half is 1/2 under the radical, so that's 1/√2. So that's a radius of something like, oh, I don't know what, 2/3 or something like that, somewhere between 0 and 1. A slope of +1. And just a side note, Zoom keeps popping up. It's been doing this all day, saying that I have low system resources. I don't think it's affecting anything on your end, but I think it's because of these web pages that I have running in the background for the technology. So if something's not coming through on your end, just give me a heads up and I can try to sort that out. But I don't think it was causing problems earlier. But anyway, for a slope of +1, what's the curve in the 2D plane along which we can say that any solution curve to the differential equation passing through that curve will have slope +1, we'll have tangent with slope +1 at that point. That is a circle of radius √2, radius between 1 and 2 units. And let's maybe do 3. For a slope of 3, that's a circle of radius 2. And let's put all of this together in a picture now. So I'm kind of interested in circles up to radius 2. And now what I'm going to do is, if I was drawing this in by hand, on paper, I would draw, say, maybe some light curves in pencil, just like very, low pressure, so they don't stand out very well. What I might do is, say, use green for this, and maybe I'll try to use, like, I don't know, like a little bit lower of a thickness of a line or something. But I'm going to draw some circles of some different radii. So here is and I mean, again, I'm not an artist, but this is my circle of radius 1. I have a circle of radius 0, so to speak, just this origin point. Circle of radius 1/√2, that's maybe like this one. Circle of radius √2, √2 is fairly close to 1.5. And circle of radius 2. So very important, two very important notes. These green curves here are not solution curves. These are not solutions to y prime equals x squared plus y squared minus 1. These are not slopes either. These are just curves that I'm putting on here to kind of help me draw the slopes, and the slopes will help me draw the solution curves. Let me switch this back to normal thickness just so I don't forget. So now I'll draw some slopes. I know at the origin, at radius 0, if a solution curve passes through there, it has to have slope -1. I'm going to draw a little line segment with slope -1. That looks like about a -1 slope. The next radius out is the 1/√2 circle, that next circle out. Any solution curve that passes through any point on this kind of innermost circle here, at that point has to have slope -0.5. So a fairly shallow slope, but negative. So I'll draw a few of those around here. So what am I doing differently than before? Before I kind of anchored on some different values for P and the slopes, and then I just copied over for the T's, right? So when I say estimated this slope, I just copied left to right. It was the same for all of the T's. What I'm doing here is I'm estimating a slope at some point on this circle, at some point on this particular isocline, and then I'm just drawing some other sample slopes that are the same slope around this isocline. Right, this circle of radius 1 over root 2, everywhere along this circle, if the solution curve passes through it, it has to have slope minus 1/2 at that point. For the circle with radius 1, that's where the slopes are 0, where I have horizontal tangents. So I'll draw a bunch of horizontal tangents. For my circle of slope root 2, or roughly 1.5. Anywhere along this green circle, I'll have slopes plus 1. So 45 degrees in the positive direction. Put one more in there. And then lastly, anywhere along that circle with radius 2, I'll have slope positive 3. So a pretty steep positive slope. My slopes are getting a little crazy. Some of them are a little steeper than others, but I think we can generally see the behavior. We have some curves that seem like they're going to go like this. I see an inflection point here, like say at roughly -1, 0. It looks like some of my curves are going to kind of come up, go down, and then back up again. And then it looks like I'm going to have some that are going to kind of skim the right side, doing something like this. So it looks like my solution will be kind of overall generally be kind of increasing left to right, but some will be strictly increasing and some will have like a little inflection point. They'll kind of dip down a little bit before starting going back up again. Seems like this would be a sampling of the different types of curves I would see as solutions. Skimming on the top, skimming on the bottom, and then kind of cutting through that circle of radius 1 where I get a bit of an inflection point, come down a little bit, and then go back up. So that's the idea of isoclines. The general idea being that we want to find curves in the 2D plane along which we have a constant slope. And really up here, for these autonomous equations, we had isoclines that were just horizontal lines. So in this new nomenclature, all isoclines are horizontal lines. Why is that? Because P prime equals C just means that Kp minus R equals C just means that equals C, which just means that P equals what? C plus R over K, right? This is just a horizontal line. P equals number. There's no explicit dependence on T. If we don't have an autonomous equation, our isoclines aren't just horizontal lines anymore. They're more complex curves in 2D space, but we find some of those curves, we take a sampling of those curves, and along each of the curves, we put in a sampling of the slopes, and then we use those slopes to help us to draw some solution curves. Any questions? Okay, so now we're going to look at using some technology to help us. So the first thing that I'm going to do is there's a Java applet that I popped into the chat here. So you can use that, or you can use any of these 3 web pages, which I'm also going to pop into the chat. So I think everybody should have access to the Java applet as well as these 3 web pages. Let me switch my share So this first web page, the one that's from Arizona, this is the one that has access to the applet. Sometimes it can be a little of a pain to get it to run on a computer. You might have to like enable Java or something. If you don't want to do that, that's not a problem. But uh, as it mentions kind of up here, there's a tutorial on if the security in your computer is not liking running random Java applets you downloaded from the internet. That's not really a problem. I just gave that to you because that's the one I tend to use. But there's also some other examples and so on this web page. But the two pages that we'll use are these two. One from, I think this is University of Arkansas. Essentially what this guy did is just clone that Java applet on a website. And then there's a Desmos one as well. This Desmos one does some things nicely, some things, at least as far as I understand how to use it, it doesn't do. So you can see it generates slope fields very nicely, but at least as far as my understanding, I don't know how to get it to draw solution curves. And maybe that's just a question of me not knowing how to use it properly, but we're going to do one of each of these on each of these two websites and just look at the technology to help us get these direction fields. Let me resize things just a little bit here. And we'll start with Desmos, where we're looking at y prime equals sine of x minus y. So note up here, it says dy dx equals g of xy. So I want y prime equals something. That's the first thing I've got to do is I got to, if I need to, adjust the form of my differential equation. So it's y prime equals something. And in this case, that's sine of x minus y. So I get rid of this stuff. And if I type in sine of x minus y, and it's not updating. Why is it not updating? I just did this an hour ago and it had no problem. Let's try x minus y. Let me just reload this. Oh, there we go. Okay, it's just going really slow. I told you my computer was warning me that it was going slow. There we go. Okay, so this y prime equals sine of x minus y. We type it in and wait for the computer to update, and we can see that it gives us a direction field that looks like this. The scale is minus 10 to 10 in both axes. Just in case yours doesn't look the same, it could be a different scale. And if I clip this, let me clip this and move it over here so that I can draw on it. Then it kind of looks to me like, and it's a little hard to tell on this one, but it kind of looks to me like there's something a little bit like an equilibrium solution. And some of these 45-degree lines, oh, went a little awry on that one. I would expect this to be periodic, right? Because I have a sine of stuff. And sine of x minus y. So like when x minus y is something like, pi, I should get slope 0. Or when x minus y is something like, say, pi over 2, I should get slope 1. So I should have, say x minus y equals pi over 2. That would be a line with slope 1, and I should have a slope, a direction of 1 in that case. That's kind of an equilibrium solution, right? Where I'm kind of staying along this same isocline here. And then in between, it kind of looks like I'm going to have solutions that look a little bit like this. these shouldn't cross one another. Any crossing is just, a little error on my part in drawing them. And then, of course, we'd have a similar set of solutions in each of these other like corridors, so to speak. I have like another corridor here where it's just a copy of that one next to it, or another one here. So I just have copies of these, of this kind of middle corridor going to the down and to the right or up and to the left. So Desmos is nice on one hand because it's, nice and pretty and colorful and all that, but it does have maybe some shortcomings. This site is quite a bit more Spartan, but it'll allow us to draw, it'll allow us to draw solution curves directly on the plot. So let's first try y prime equals sine of x minus y here. Note that here dy dt, so our independent variables t, dependent is y. So sine of t minus y. And I'll just leave all the rest of this alone and I'll graph the phase plane. And I see I get something pretty similar to over here. The scale's a little smaller, so looks a little bit different, but I do see this kind of this corridor, same behavior in the middle. And one of the super nice things is I can just pick a point in here and click, and it'll give me the solution propagating to the right and to the left. So those are my solutions. If I try to get right on one of these curves, I didn't get it quite perfectly, but we can see that that's pretty much that straight slope one isocline. And same down here, if I try to get pretty close to this one, that's pretty much that slope one isocline. And then I have another copy of that same corridor down here, another copy up here, and so on. So this is probably my favorite one because you don't have to have any Java applet or anything like that. And you can just click a whole bunch of random points on here and plot a bunch of solutions. You get an idea of what the direction field in general looks like, so you can tell what are the interesting points, and you get a lot of solutions this way really quickly and easily. And again, as far as I know, like one downside of this is I don't think there's a way to actually clear the thing other than just graphing the phase plane again. So I don't think you can like clear one solution or something, but we can just regraph the phase plane and that erases all of our solutions. So if I consider this second example over here, I need dy dt equals something. So I need y prime equals negative y squared over x squared. So I just have to put it in the right form. Negative y squared over x squared. Let me close Desmos just because I think it's using a bit of memory, slowing things down. So if I do negative y squared over, and then my independent variable is t squared. If I graph this one, and now I look at this and I say, okay, I think there is some interesting behavior in each of the four quadrants. So I might pick a couple solution curves in the first and third quadrants. It does kind of seem like there is an isocline like y equals negative x. For some things like this, it's really hard to get a really clear isocline going all the way down here. Maybe something like that is not too terrible. Anytime that we're doing kind of numerical analysis of differential equations, there are a whole bunch of caveats and a whole bunch of pitfalls and so on. And we're seeing a little bit of that here with these kind of crazier looking solutions. But we generally see that in the second quadrant, solutions tend to go towards 0, 0. In the fourth quadrant, solutions tend to go away from 0, 0. In the first and third quadrants, they kind of come in towards 0, 0 and then get pushed away. This is what 0, 0 is what we would call a saddle point, where kind of in one direction we have stability in a sense where solutions get pulled into it, and in the other direction we have kind of anti-stability, solutions getting pushed away from it. But we can see this is an interesting differential equation to plot over here. And we could look at something like this one as well, just to check our work. So y prime equals x squared or t squared plus y squared minus 1. And if we graph this, we see this similar behavior. We have some solutions that kind of just skim this kind of circle here on the left, or on the right, sorry. Some that skim it on the top left. Whoops. And then some that have an inflection point kind of cut down into that circle and then continue going up on the other side. Any questions on anything that we talked about in direction fields or slope fields? Okay, let me get my share back together here. Let me just erase this picture so it's not taking up a bunch of memory. Okay, so now moving on to separable equations. So we looked at an example of a direct graphical technique. We'll talk about Euler's method, a numerical technique briefly in the supplement that's kind of directly related to direction fields and slope fields. But then moving on to separable equations, the goal here, we're starting to move into techniques where the goal is to get an algebraic solution. If all else equal, if we had a choice, we prefer the algebraic solution almost all the time, because from the algebraic solution we can create a table of values. From the algebraic solution we can create a graphical representation of some members of the family of functions. So how can we find an algebraic solution? Well, I suppose we already saw our first technique, which was just the kind of guess and check technique. But obviously that's not really always going to work. So what's another technique that we could use? Here I have a motivating application. I'm not going to go through this just for the sake of time. But if you want to read through the details after we cover this topic, you might find it interesting. This is an example of motion of a falling body in the presence of air resistance. But let's jump down to this equation here. dy dx equals e to the x over y squared. You zoom in a little bit further. And the trick that I'm going to do in separable equations, we're going to talk about like why we can do this in a bit. But I'm going to treat dy dx remember, this symbol, dy dx, is a notation. It's a symbol that means a certain thing. It's not a fraction or whatever. Dy horizontal line dx means a certain thing. It means the derivative of y with respect to x. It means the same thing as y prime or whatever other symbol I might want to give it. But obviously this symbol is motivated by a fraction. It's motivated by the limit of delta y over delta x as delta x goes to 0. Can I maybe cheat a little bit, treat it as a fraction? Can I treat this as like a ratio of two differentials? Because dy is a differential and dx is a differential. Can I treat it as a ratio of differentials? What happens if I do? Well, maybe I could multiply through by dx. I've got a bunch of x stuff on the right side. There's a y squared on the right side as well. Maybe I can multiply through by y squared. I have now separated my y's from my x's. Right? Just some basic equation solving steps. If I can treat dy dx as a fraction. I've got the y's on one side, the x's on the other side. But I have these annoying differentials, dy and dx. How can I make sense of those? I can make sense of them if I integrate both sides, if I put an integral sign on both sides. Note that on the left, I have integral of, this very important, integral of y squared dy. This is going to be 1/3 y cubed. On the right, I have integral of e to the x dx. I don't have like integral of, x squared dy or integral of e to the y dx, where I'm mixing my variables. And my integrand on the right-hand side only has x's, my integrand on the left-hand side only has y's. So we call this a separable equation because we can separate the y's on one side and the x's on the other. So this is, of course, e to the x. And I'll throw on a plus c, my arbitrary constant on the right. I could have put an arbitrary constant on the left as well, but then I could just subtract d off of both sides and fold that into the single arbitrary constant c. So I'm just going to put one arbitrary constant at the end. Or this tells me that y cubed equals 3e to the x plus some other constant. I'll call it c tilde. So 3 times the original constant. Or y equals the cube root three e to the x plus c tilde plus whatever constant we're calling this. And this is my family of solution curves. Let me try to close down a couple more web pages because OneNote is starting to kind of jump around on me a little bit. So this is my family of solution curves. If I choose c tilde equals 0, y equals cube root of 3e to the x, that's going to be one solution curve. If I choose my constant to be 1 or -10 or plus pi or whatever it is, that'll give me a different solution curve. And I could check that if I do y prime, I get e to the x over y squared. I'm not going to go through that check, but you could take the derivative of this function with respect to x, and then make sure that you get e to the x divided by this thing squared. So what's the general idea for a separable equation? If we have dy dx equals f of xy, where f is, say, g of x times p of y, we call the differential equation separable. If our right-hand side is the product of some stuff with x times some stuff with y, then we can separate this way. If dy dx is g of x times p of y, we get dy over p of y equals g of x dx. We integrate both sides, and this gives me an implicit relation of y with x. So you get some h of y equals g of x plus c. Let's look at another example. So here we have dy dx equals 3x squared plus 4x plus 2 over 2 times y minus 1. And we have a little bit of additional information here. Y of 0 equals -1. Remember, when I do that, I have a first order equation. I kind of either implicitly or explicitly do an integration to get rid of that derivative. That spits out a plus c. That makes a family of functions, a bunch of functions that are solutions to this differential equation. But then if I remember that this family of functions, they don't cross one another, at least typically. They don't cross one another. So if I pick a certain point, just like I did in that direction field, was it University of Arkansas or something? In that plotter, when I picked a point, it could go to the left and to the right and say which member of the family of functions was associated with that point. It could draw that curve. So the differential equation has a solution that's a family of functions. But this extra piece of information picks out a single member of that family as the solution. Right? If you think of, say, like a mass spring system, and you say, if I pull the mass down a little bit and push it up before I let it go, it's going to do something. Or if I push it up and just let it go from rest, or if I, hold it at equilibrium, but, push it down and then let it go. Those are all going to be different ways that system could evolve in time. But if I tell you what I did at the beginning, then you can decide which specific propagation your system is actually going to undergo. So this piece of information here, we call it an initial value. So in other words, we're saying at position x equals 0, y has to be -1. Or I'm looking for the member of this family of functions that also goes through 0, -1. As a side note, we still call it an initial value, even if the value of the independent variable is not 0. But this problem as a whole, we call an IVP, an initial value problem. A differential equation coupled with an initial value. The differential equation gives us a solution of family of functions, and the initial value tells us which member of that family of functions we're interested in. So let's solve the differential equation. We can see that we have dy and 2 times y minus 1 can multiply across equals this quadratic times dx, which we're going to multiply across. Again, we haven't really talked about why we can, in a sense, multiply by this dx. But for now, we're just going to do it, and we'll take care of that detail later. I'm going to integrate both sides. And if I integrate this, I think I get just y minus 1 squared. On the right-hand side, if I integrate, I get x cubed over 3 times 3. So just x cubed. I get x squared over 2. So that's plus 2x squared. Plus 2x and plus c. Y of 0 equals -1. If I want to get this as y in terms of x, maybe I'll do y as 1 plus or minus square root of x cubed plus 2x squared plus 2x plus c. So I could write my family of functions this way, parameterized by c, or I could leave it implicitly that way. Either way is probably fine. Obviously on WebDesign or something, write it in the way that it tells you to. If it gives you different choices that are implicit functions, pick the right one, or if it says write it explicitly, write it explicitly. Here, y of 0 equals -1. What's y of 0? It's 1 plus or minus square root of c. Since this is an implicit relation, kind of like a circle, right? For given inputs, I can have, or for a given input, I can have different outputs. And I want this to be -1. So what does c have to be? C has to be, c has to be 4, so that I get 1 plus or minus 2, but I also have to be on the negative leg of this, right? So c is 4, and I'm on the negative side of this. So I have y equals 1 minus square root of x cubed plus 2x squared plus 2x plus 4. This is the particular function that is a member of this family. In other words, that's a solution to this differential equation, and also passes through this point 0, -1. Any questions so far? So I'm going to jump down here really quickly just to take care of this detail. Why can we multiply by dx? And here's the formal kind of rationale. And what it amounts to is just using the chain rule, aka the substitution rule. And if we go through, we see that in the end, we end up with something that's effectively just like we multiplied by dx. So when we say up here multiply by dx, we're not really multiplying by dx. We're saying, go through and use the chain rule and slash substitution rule. Oh, that turned that into a fraction instead of just the slash. It should be chain rule slash substitution rule. But it's just basically a shorthand notation for using that. So here's the rationale for why that's a legitimate thing to do. And let's work through one more problem. We only have a few minutes left, so we'll jump down to this one. So fairly famous problem, dA dt equals lambda a. We might be able to guess the solution to this. In fact, I think we had previously guessed the solution to something similar to this. A prime equals a. Obviously, the solution is an exponential. A prime equals lambda a is going to be closely related to that. But let's generate that solution from the separable equation method. So I get dA over a equals lambda dt. And then I want to integrate both sides. So I've separated my a's from my t's, my dependent from my independent variables. I integrate both sides. 1 over a dA is log absolute a. Integral of lambda dt is lambda t plus c. Or I can exponentiate both sides and I just get a of t is e to the power lambda t plus c. I'm not really worrying about the absolute value here. I suppose I can make it like a plus or minus or something. But quite often in these kind of problems, we're thinking of A as modeling the amount of something. So this might be the amount of individuals in a population, or this might be, say, the amount of radioactive particles in a substance. So we might be thinking of radioactive decay here, where lambda would be some negative constant. Note that A of 0, this might be an interesting thing to know. At time 0, what's the amount that we start with? Is e to the 0 plus c, it's e to the c. I'm going to just call this a naught, or a sub 0. I also notice that e to the lambda t plus c is just e to the lambda t times e to the c. And e to the c is a0. So A of t is just a naught e to the lambda t. So sometimes for my family of functions, when it's parameterized by a constant that doesn't really mean a whole lot to me, I don't really understand what c does. Sometimes I can reframe it, and my constant here is a naught. Note that a naught is e to some constant, so it's bigger than 0. That's my initial amount, my initial number of radioactive particles that are decaying, or my initial number of people in the population or something. It's not any, theoretically better or worse to write my family in one way versus the other, but the second is probably more meaningful. I understand what a naught is, that's the initial amount. Where up above, I don't really have an intuitive understanding of what c is. All right, and I think we do have time for one more. So if we do this one quickly, I see x over 1 plus x on the right. So if I have 1 plus x over x dx, and here we have dx dt. So x is the dependent variable, t is the independent variable, equals 2t dt. We want to do the integral on both sides. On the left, I note that I can do an algebraic simplification, make this just 1 over x plus 1. So this is log absolute x plus x. That's going to be equal to t squared plus c. And note, if I wanted to solve explicitly x of t equals something, I really just can't do it. Sorry, my allergies are going kind of haywire today. So I can't really get x of t equals something. So how then do I interpret x of 0 equals 1? I interpret it as being when t equals 0, x equals 1. So in other words, this is my family of functions to plug in my specific plane I'm looking for. Everywhere I see a t, I plop in a 0. Everywhere I see an x, I plop in a 1. Not really a big deal, right? But if you haven't kind of seen this before or thought about it, you might say, wait, I can't get x of t explicitly. What do? Well, just do it this way, implicitly. This is 0. So I get 1 equals, this is 0, c. So log absolute x plus x equals t squared plus 1. That's the solution to the full initial value problem. This is the family of functions representing the solution to the differential equation. And this is the particular member of that family that goes through the point t equals 0, x equals 1.